Hello everyone, welcome to GChem classes. So today we are going to see the next part. We are going to see the vibrational frequency. Okay, vibration. We have already completed our Beer-Lambert's law. We have solved based on those problems. We have completed our rotational spectroscopy. Based on that, we have solved the problems. Because spectroscopy I have just subdivided, so it will be easy for you, right? So from which section questions are coming. And wait for my upcoming video, which I am going to discuss you from which topic, from which topic, how many questions they have asked, and what all those questions. Okay, so it will be detailed analysis before your examination, so you can directly put revision on those particular topic, and you can go for the examination, correct? So in my full potential, full energy for your upcoming examination. Okay, so in return I need your result, right? So whoever is watching this channel, I need 100% success rate for them, right? So whatever questions, whatever doubt you have, you can directly ask me. So it will be beneficial for you, and it will be a great satisfaction for me that I have helped you in this upcoming examination, correct? So let's start the vibrational spectroscopy. Okay, for your examination, no need to study in detail. Okay, you should know the basic concepts, correct? Whatever the questions, if you are analyzed in correct way, you will find that they have asked only basic concept based on those examples. Okay, like if you know all the basic concepts, like whatever the topic they have given for IIT JAM 2023 in syllabus, so you will easily get 50 to 60 marks, correct? And out of that 50 to 60 marks, if you are watching my all the videos in the IIT JAM folder I have created, based on those concepts, I am not talking about those questions, based on those concepts, easily you will get 35 to 40 marks. Okay, let's see after examination we'll meet, and then how much percentage it came, we'll discuss it, correct? In this vibrational spectroscopy, molecule should have a dipole change, correct? What is the condition? Molecule should have dipole change. It means it should have dipole moment, otherwise it won't show vibrational spectroscopy, correct? So likewise microwave, here also this condition is there, so it should have dipole change, then only it will show vibrational spectroscopy. And one more thing, these are two types. One is stretching vibration, okay, and another one is bending vibration. Okay, so stretching vibration, bending vibration. Okay, stretching vibration means suppose this is the bend, this is the bond. Okay, so suppose this is carbon dioxide, this is stretching. Okay, and again it is coming back. These are the stretching vibration. Okay, and what about the bending vibration? See, suppose, okay, we'll see. If it is coming down, again it is coming down. Next time again it is coming up. Okay, this is your bending vibration, correct? So you have to, like, they will ask you question based on this particular molecule, how many stretching vibrations are there, how many bending vibrations are there. So just remember, yesterday's class I have taken you for degree of freedom, right? Based on degree of freedom, like what is the formula, like why it is important, the degree of freedom, why it is important, we'll see. Degree, I'll just write F. So degree of freedom equal to we can say for linear. Okay, first we'll say degree of freedom, it includes translational degree of freedom plus rotational degree of freedom plus translational degree of freedom, rotational degree of freedom, and then last one, the vibrational degree of freedom. Okay, so if you are concentrating on this vibrational degree of freedom, you have to do subtract this translational, you have to do this subtraction of rotational. Okay, then only you will get the vibrational degree of freedom. And then in this vibrational degree of freedom, again you have to subdivide by one stretching and second bending. Okay, how many stretchings are there and how many bendings are there, that you have to subdivide it. Okay, so these questions they might be asking you. Next we'll see the Hooke's law, because that is important. They have asked question based on Hooke's law. Okay, so we'll see what is Hooke's law. Okay, so in this Hooke's law, I'll not going to derive it because it will take much time. So now you don't have time, right? Much, because you have to do revision and revision. Okay, so two things you just remember. Okay, this revision should be in consistent manner. Then only you will succeed it. Consistency is very much required for your success. Correct? So Hooke's law, directly we will write the formula like Hooke's law. The wave number 1/2 pi c under root, what is that, k bate mu. So just we will discuss all these things, you will get to know. Already you have seen this mu. This is nothing but reduced mass. Okay, and you know the formula of reduced mass, m1 m2 divided by m1 plus m2, right? What is this? This is force constant. This is force constant. For any bond or any spring, we have that force constant, right? So how much it will pull, how much it will go. So based on those constant, okay. And what is this c? C is speed of light. Okay, so these are the factor. Okay, based on that you are just finding the wave number. Sometimes they might ask you for isotopic problem, right? Suppose it is having HCl and it is having DCl. (35) or maybe they give 36, whatever problem, maybe it is 35 only, because here the isotope is changing, no? So what will happen for their force constant changes, okay? And what the first problem will be, what is the difference of force constant, ratio of force constant. Second will be, what is the difference of wave number, okay, the per centimeter value. They might be asking this type of question. We will solve it, okay? So next, first we will see the concepts and then we will directly go for the your PYQ. Now we are just drawing the anharmonicity, okay. All students are familiar with this type of graph, correct? You know, right? This point we are saying that it is a equilibrium bond length. This is a potential energy, and this curve we call Morse potential diagram, right? Okay. Clearly we will write it. First difference will be more, then second, then third, fourth. Likewise it will be, okay. This is the bond breakage, okay. So this will be vibrational level 0, vibrational level 1, vibrational level 2, vibrational level 3. Likewise it will go vibrational level, okay. So with this Morse curve, this is anharmonic oscillator, okay. If you want to draw harmonic oscillator, you have to do this one, okay. This will be harmonic oscillator, correct? And this one is anharmonic oscillator. What is the selection rule? First, one by one we'll see what all we can get it from this Morse potential diagram. What is the selection rule? It will be, okay, delta V equal to del V equal to, it will be plus or minus 1. Okay, means it can move from here to here, it can move from here to here, or if it is moving from V0 to V2, then we call it first overtone. Okay, if it is moving to 0 to 3, then it will be second overtone. Okay, if it is moving from first to third, it will be first overtone. If it is moving from first to fourth, it will be your second overtone, correct? Likewise, and this vibration, this the absorption of energy, and when it is going from V equal to 0 to V equal to 1, we called it fundamental vibration. Okay, these questions they might ask that for fundamental vibration, which one will be the correct answer? So V1 to V0, option A. Option B will be V0 to V1. Option C will be V0 to V2. Option D will be V1 to V2. So fundamental vibration will be this one, option B, correct? So fundamental vibration will be option B. So this you keep it in mind. And one more thing, it will come from this Morse curve diagram. We'll find out the energy level, how we are finding energy for just, if we are finding En will be n plus half and then h nu. Okay, this is the energy, and n is like v equal to 0, you have to put 0, v equal to 1, you have to put 1, and here also it will be 1. If it is 2, here also it will be 2, and here also it will be 2. And two successive energy differences. What will be the two successive energy differences? If you are just writing 0 energy, like energy 2 to 1 or 1 to 0. If you are saying 1 to 0, how much it will come? It will be your, just we'll write it down. First this part we have to write. So it will be 1 plus half h nu minus, here n barabar 0 plus half into h nu. So how much it is coming? It will be 3 by 2 h nu minus, it will be 1 by 2 h nu equal to, it will be 3 by 2 minus 1 by 2. How much it is coming? 3 minus 1, 2. 2 and 2, it will be divided by 1. So 1 h nu. So it will be h nu, correct? So the fundamental vibrations value we got it. How much? H nu. Okay, h nu. Okay, fundamental vibrations value. And now what is the value of this n? N will become 0. So it will be 0 plus half h nu. How much it is coming? It will be 1 by 2 h nu. So this value is your 0 point energy. And why we call it 0 point energy? Because for a particular bond there won't be it won't be, the value, vibrational value won't be 0, correct? Because the bond will have some particular energy, correct? So their energy should not be 0. It won't be like, this is the potential energy curve, right? So this place it will be 0. So it won't touch here. See, when it is touching here, it means vibration, equilibrium vibration. So you just see from here to here, it is a bond length, correct? And suppose it is HCl. Okay, in this bond, it is not fixed. It will always vibrate it. Whether if it is getting minimum energy also, it will vibrate it. Okay, so this is your vibrational level for 0 point energy, correct? This is only 0 point energy or 0 point energy. So in this 0 point energy, your value will become 1 by 2 h nu. Okay, so it means the vibrational level, okay, whatever the vibrational level, it won't be, it never be 0, correct? It will have some value, always it will have some value, whether you are in vibrational level 0. Okay, so maybe they might ask this question, 0 point energy, correct? And then what else we can get it from this Morse curve? Just we'll discuss one thing. See, this is the equilibrium bond length. You have increased some of the potential energy, like this much energy you have increased. This is the basic energy. So in this, it is giving 0 point energy. Suppose you have increased energy from potential energy from here to here, right? This much energy you have given. So once the bond has received this much energy, the vibration, see the bond, initially the bond were vibrating from here to here, right? Like this vibration were taking place. Now once the energy is reached, this vibration increased and it reached till here, right? See the vibration, the bond length has increased based on vibration. Again you increase the energy, and once you reaching this much energy, what is happening? This vibration is taking place. So once it is, okay, going far away from this hydrogen and HCl, that bond get break potential where it can hold that much energy. Okay, if you are giving more than that energy, what will happen? That bond itself will get break. Okay, it won't have that much capacity to hold this energy. So this part we called it, this much energy we called it bond dissociation energy. Okay, okay, this is bond dissociation energy. Okay, this point is a bond dissociation energy, because this much energy if you are putting, this bond won't be stable. It will just dissociate, and the hydrogen and chlorine will be separated out, correct? So this much we are getting from Morse potential diagram. I think you might getting 1 or 2 questions from here. So whatever questions you are getting, it will be fulfilled with this concept. We'll move to the next topic, that is some value we will see for like per centimeter value, where the peak will come, okay, that the absorption peak will come, correct? So before that, just we will divide this IR radiation in two subdivision level. One is from 660, okay, it is from 660 to 4000, okay, 4000 per centimeter. Here also it is per centimeter. In between, if you are coming here, it will be 1500 per centimeter. So it has divided into two parts. This we call fingerprint region. This will call functional group region or stretching frequency we can call. So functional group region. Okay, this is functional group region and this is fingerprint region. So what we know in this fingerprint region, what we'll come to know from this fingerprint region, here we'll see the bending vibration, okay, and here we'll see the stretching vibration, okay, here we'll see the stretching vibration, here we'll see the bending vibration, okay. So 660 to 1500 per centimeter will have your bending vibration, or we call it fingerprint region, okay. Directly, if they want, directly they can ask this question. And in this functional group region, the important part is this functional group region, where it is start from 1500 per centimeter to 4000 per centimeter. So in this region, some important functional group I am going to discuss it, which like I have seen that those functional group only they are giving and they are mixing with the NMR and they are asking question, correct? So first will be your carbonyl stretching. Okay, carbonyl stretching, it will start from 1600 per centimeter to 1750 per centimeter, okay. So 1600 per centimeter to 1750 per centimeter, and then peak will be like sharp, okay. You will get sharp peak, okay, you will get sharp peak at 1600 or 1750. Suppose in this place we will say it will be like this. Suppose this place is 1600 to 1700. 1600 to 1750. So you will get this kind of peak. So this is, if you are getting this kind of peak, make sure that you will have one carbonyl group, okay, whether it's a carboxylic, whether it's a aldehyde, ester, okay, acid, but one carbonyl group is there. To confirm whether it's a oxalic acid or maybe it is aldehyde, what we know, just see the second peak for OH. See, if there is no hydrogen bonding, if hydrogen bonding is missing, then you will get peak at 3600 per centimeter, correct? And the peak nature will be, suppose this is 3600, the peak nature will be like this, okay, sharp, single line, okay. And suppose you have hydrogen bonding. Now you have hydrogen bonding. Suppose if it is a carboxylic acid, it will have hydrogen bonding, correct? So I'll discuss the example where hydrogen bonding won't be there. Okay, I'll just discuss the OH functional group and there won't be any hydrogen bonding. I'll discuss that example. So hydrogen bonding, if it is present, it will start from 3300 to 3600 per centimeter, and the band nature will be, this band nature will be sharp. This band nature will be also sharp. This will be broad. Okay, broad band. How this nature will be like, from here it is starting 3300 and here it is ending 3600, right? So it will be like, correct, it will be like this broad band, okay. You won't find any single place from where to draw the peak value, okay. See, for this you have, for this you have, but for this you don't have. So you have to take from here to here and see the range. If it is falling between this range, you have OH, okay, in your molecule. If both the peak you are getting, this one and this one, broadband, and this sharp peak at 1600 to 1750 per centimeter, confirm it that, like, it is confirmed that you have carboxylic acid, correct? So likewise you have to discuss it. There is no fixed value where you will memorize and you will go whether it is coming in this value. So it will be like you are getting this peak, correct? There won't be any fixed value. It will be little bit here and there based on the electron density, correct? But it's a general values. With this you can easily calculate it. Okay, so as I told you that I'll give you one example where hydrogen bonding won't be there. Let me draw that example. Suppose you have this molecule where you have tertiary butyl group, and OH you have here, right? So For the second molecule of this similar molecule, see, due to this steric hindrance, okay, due to this steric hindrance, that OH can't come near to this OH, right? So it can't be form a hydrogen bond because of steric hindrance, okay. So this OH will show a sharp peak. Maybe in this examination they might ask this question that one OH is there, like OH is there, but it is showing sharp peak. Which one will be your correct option, right? So this will be your correct option. Just see that OH should be in between the steric part, okay. So the second OH can't come and form a hydrogen bond, right? So now directly we'll take the examples and we'll solve those examples, okay, one by one. Let's see. Then after NMR, directly we'll go to the organic chemistry, because many are asking for organic chemistry. Then we'll go to quantum chemistry, correct? So question 2020, question number 12. So 2020 question number 12 we have, you can see in the screen, the force constant for see, it is given H 35Cl and D 35Cl are the same and both can be considered, okay. Force constant, they are saying that it is same. This also both the force constant is K only, okay, it is same, and can be considered as harmonic oscillator, okay. This is not an harmonic oscillator, harmonic oscillator they are saying. And HCl has a fundamental vibrational transition at, so fundamental vibrational transition, so V 0 to 1, okay, this value they have given 2886 per centimeter. This is a fundamental vibration transition. The ratio of the 0 point energy, they want 0 point energy ratio, okay. So this fundamental vibrations they have given, based on that you have to take the ratio of the 0 point energy of HCl to the DCl, okay. So 0 point ratio for HCl and DCl, this ratio they want. So we know that force constant, how this force constant will come, we will directly see this mu bar equal to, we know that it is 1/2 pi c under root k bate mu, okay. So directly we will write mu HCl, and this is for HCl, and the second will be, this will be equation 1, and second will be DCl 1/2 pi c under root k bate mu DCl, and they are saying that these two are similar. So this will get cancelled, like what we'll do, equation 1 and equation 2, just will equate both the equation in one place. So what will happen, 1/2 pi c under root k bate mu HCl equal to 1/2 pi c under root k bate mu DCl, okay. So what is happening, this will get cancel it out, this k will cancel it out. So what is here, mu HCl divided by mu DCl will be, because it is in down, so the next part it will be in reverse, right? So here it will be mu DCl divided by mu HCl, correct? So this equation you have got. Now your like job to find out this mu, because we have to calculate that mu and then directly we'll put it here, we'll get the ratio, correct? Okay, just we'll calculate for reduced mass. Okay, what is the reduced mass? We'll see. Mu HCl, how much it is coming? It will be M1 into M2, so it will be 1 into 35. They have given 35, so don't consider 35.5 because they have given 35. If you are considering 35.5 also, it won't be any effect, because you are taking ratio, right? Here you have to take 35.5. Here also 35.5 you are taking, so there won't be any problem. So 35 divided by 1 plus 35. So how much it is coming? 35 divided by 36. So 1 you got, and mu DCl, how much it is coming? 2 into 35, because deuterium, okay, D is deuterium, divided by 2 plus 35. So how much it is coming? 70/37, correct? So we have calculated this value. Now we have to find the 0 point energy ratio, right? So 0 point energy ratio will be, we know that for 0 point energy, how much it is coming? 1/2, and then it will be your h nu, right? Okay, 0 point energy is this one, h nu. So nu, this you write it for 0 point energy for HCl, you write it HCl. For 0 point energy For DCl, you write 1/2 H nu DCl. Now just try to find the ratio. So 0 point energy of HCl divided by DCl will become 0 point energy, like the formula, it will get cancelled out. How much it is coming? HCl divided by DCl. So again this formula it has came. So just put this value to this formula. How much it will come? See, under root DCl 70/37 into your 35. So 36 divided by 35, it is 2. So how much it is coming? 72 divided by 37. Okay, so 72 divided by 37, how much it will come? I have already calculated. 1.9466. 1.9466. Now what will be the value of, if we are removing that under root, if we are removing that under root, what will be the value? It will be 1.395. 1.395. Okay, so which option will have this one? 1.395. Option C. Okay, so your correct answer will be option C. Good. So we'll see the next question. Question number 3 from the 2019. Okay, next question is from 2019. Question number 3. Okay, you can see in the screen. Question number 3 from 2019. The number of vibrational mode of a carbon dioxide molecule that can be detected using infrared spectroscopy. So carbon dioxide, you know, right? See, we know that it is a linear. Okay, if it is in linear, if it is having the symmetric stretching, it won't have permanent dipole moment, right? If it is going this side or if it is going this side, what will happen? Mu equal to 0, and once mu equal to 0, it won't be active. Okay, it won't be active in your infrared. So we'll see when it will be like this bending vibration, only bending vibration if it is having. Okay, like this. Okay, bending vibration if it is having. If it is having, if it is carbon is coming down, oxygen is going up. Okay, so if this type of bending vibration is there, those bending vibration only your IR active. Okay, infrared active. So based, like, for that we have to calculate. Okay, so carbon dioxide molecule that can be detected using infrared spectroscopy. Okay, so it is not asking total vibrational mode of carbon dioxide. It is just asking those vibrational mode of vibrational mode which are infrared active. Okay, so this linear one we no need to take. So if you are taking for linear, you will be misleading to your answer, correct? Because linear is infrared inactive. So you have to take non-linear one. Why non-linear one? Because if you are taking non-linear, only non-linear is infrared active, correct? Linear one will have 0 dipole moment and it won't be active. So for non-linear, we know notional degree of freedom will be 3 and minus. For non-linear, it will be 6, right? So 3 into how many atom are there? And n value is 2, 1 and 3. So 3 into 3, 9 minus 6 equal to 3, right? So your option C will be your correct answer. Suppose if you are taking linear, what will happen? See, if you are taking linear, so vibrational will be 3 into 3 minus 5. So how much it will come? 4. And then you will mark option D. But it will be incorrect because linear one won't be infrared active. Okay, because they have mentioned in question that it should be infrared active. Okay, detected using infrared spectroscopy. So likewise they will just modify their question. So be clever and find it out the modification, what modification they are doing in the question paper, correct? So next question we'll take it from the same year, I guess question number, okay, question number 12. Okay, so question number 12, what they are saying, let's see. From the same year they are asking, 2019. Question number 12. The correct option for the number of bending modes of vibration in each of H2O, only bending mode of vibration they want, H2O, CH2 and SO2 molecules, right? Only bending mode of vibration they want. So just we will find out first vibrational level. We know that this one is linear, that much you have to know, right? This is linear, this is bent, and this is also your bent. Okay, So this is bent, means this one is non-linear, not required bent or anything. Just divide with non-linear and linear. This is non-linear. This is also non-linear. Okay. So for this H2O, vibrational degree of freedom will be 3 and 3n minus 6. For this, it will become 3n minus 5. Okay, because it is linear. For this, 3n minus 6. Now just find it out. All the vibrational mode I am just finding out. I'll just put this line. So 3 into, how many are there? 3. So 3 into 3, 9 minus 6 equal to 3. Here it will be 3 into 3. So 9 minus 5 equal to 4. Here it will be 3 into 3. So 9 minus 6 equal to 3. So all we got vibrational degree of freedom is 3, 4 and 3. But in this we have stretching also and bending. Okay. But what they want bending mode of vibration only. Okay. Bending mode of vibration. For H2O will have stretching vibration number 2 and bending vibration number 1. Okay. Stretching will be always 2, because if we draw this molecule, this will come this side. This is 1. In this 3 only we have to fix it, correct? So now for this CS2 we have 2 stretching and we have 2 bending. Okay, total 4. And this SO2 will have again 2 stretching and we have 1 bending. Okay, these many questions we were having from PYQs. So as I subdivided, that's why question number is less. Otherwise from spectroscopy there were almost each year they have asked 5 questions. Okay, 5 to 6 questions they have asked each year. Okay, but I have just divided. So now left over is NMR. So after NMR directly I'll go for organic chemistry. If you really like this class, kindly do share to your friends. Thank you for watching. Thank you.